Welcome back to part 2 of chapter 13. This is the last video of unit 3. So in our last video, we wrapped up talking about what a good randomized comparative experiment looks like. So in order to have a good, valid randomized comparative experiment, the study is expected to be randomized, comparative, placebo-controlled, and a double-blind experiment. Now, to reiterate the point from last video, we brought up the idea of blocking. So when groups of experimental units are similar, it's a good idea to gather them together in blocks. So blocking is for experiments what stratifying is for sampling, if that helps make a connection. The layers that are common, we want to kind of group those together. So both methods group together subjects that are similar and randomize within those groups as a way to reduce unwanted variation. So oftentimes the phrase goes, block what you can, randomize what you cannot. And this idea is that we try to control for as much variation as possible, and then we trust in randomization to shuffle things up enough for any unknown other variation that we are not accounting for and not what we're studying. So the study of statistics is a study of variation. And probably the most important purpose of control in any study is the attempt to reduce variation, resulting from any variable other than that variable of interest and being observed. All the methods we have discussed are attempts to reduce unwelcome variability. So all of this fluctuation and change, as much as we can control that in an experiment, that allows us to make inference conclusions on our findings. So blocking isolates the variability due to the difference between the blocks to highlight the differences due to the treatments. So if we go into these different blocks, now we can just measure the effects of the treatments that we have on these differing groups. We use blocks, again, to reduce variability. So we can see the effects of the factors by separating the effects of the blocks themselves. So by blocking, now we can just look at the factors in each of the disparate groups to see if this has a true impact. Research randomly assigns subjects within the blocks, and we call the design a randomized block design. So for example, if we were concerned about the effect of grade level on our experiment, we could block by grade level, then randomly assign subjects within each grade level to the various treatment levels. So suppose we are interested in the effect of an SAT prep class on SAT scores. Further, suppose we wonder if the year that students takes the course affects the SAT results. So we know we offer an SAT prep class for 0 hour at our school. So we might block our subjects by junior and senior to control for that variability due to the year they graduate. So our experimental units are students at DCHS, and we would call these subjects. Our treatments are SAT prep course and no SAT prep course. So either you take the 0 hour or you don't take the 0 hour class. Our factors affecting SAT scores are a lot. I mean, there's IQ, motivation, courses taken in high school, study habits throughout high school, and so on. So to control all those factors, we will randomly assign students to the 2 treatments. And this is what makes this an experiment. The response variable will be SAT test scores. That's what we will see and measure after we've implemented this. So this is what a diagram of this blocked experiment looks like. It's blocked by grade level. So we take our pool of students, let's say 60 students that want to take this course. And of course, not everyone can take it. So what we do is we have 30 seniors and then 30 juniors. Both of those are students that want to take the SAT prep class. So from those 30 seniors, and those 30 juniors, we are going to randomly assign who gets into the class and who doesn't. So we want to have a class size of 30, and so we'll have 15 in not taking the class and 15 in the class. Notice we indicate our random assignment. And this is me walking you through what I expect you guys to be able to do. Same thing with our juniors. We take them and we randomly assign 15 no SAT prep, 15 with the SAT prep. And then what we're going to do is we're going to compare the results from those blocks. So we're going to compare our SAT and no SAT prep class for both juniors and seniors and see if there is an effect from Mr. DF's SAT 0-hour prep class. So that is the design I want you to be able to create when looking at an experiment. Other types of experiments that we will see. So this next thing is matching. In a retrospective or a prospective study, subjects are sometimes paired because they are similar in ways not under study. So like twin studies are a good example of this. Other things that are like pre and post tests are really good matching because you're the same person. You took the test before you learned anything. You took the test after you learned something, and we can compare those results. So matched pairs design creates blocks by matching pairs of similar experimental units. Chance, and by chance I mean random assignment, decides which member of a pair gets the first treatment. The other subject in that pair gets the other treatment. For example, suppose researchers want to know how a new diet affects weight loss compared to a standard diet. Since this experiment only has two treatment conditions, either a new diet or a standard diet, they can use a matched pair design. If they recruit 100 subjects, then group the subjects into pairs based on their age and gender. So for example, a 25-year-old male will be paired with another 25-year-old male since they match in terms of age and gender. Likewise, a 30-year-old female will be paired with another 30-year-old female since they also match on age and gender, and so on. Then, within each pair, one subject will randomly be assigned to follow the new diet for 30 days. The other subject will be assigned to follow the standard diet for 30 days. At the end of the 30 days, researchers will measure the total weight loss for each subject. So probably the most common type of matching is the before and after, what I said, pre-test, post-test. Each pair in the matched pair design is actually just the person taking the test. And that subject gets both treatments, one following the other. So in that case, in a pre-test, post-test matched pair design, each participant serves as its own control. The order of the treatments may influence the response variable, so we must randomize the order of the treatments for each subject. So I'm sure everyone is familiar with the alcohol and driving studies. Drive to set a baseline, drink, drive again to find the effect of alcohol on driving ability. This is this idea of pre-test, post-test. Okay, so these are all fine and good, but in the real world, it's more complicated. So it's often important to include multiple factors in the same experiment in order to examine what happens when the factor levels are applied in different combinations. So on the next slide, I'm going to show you a picture of what the book talks about. The following diagram shows a study of the effects of different fertilizer and water combinations on the quality of tomatoes. Ugh. In this example, from your text, the combination of watering and fertilizing are compared for the effects on the juiciness and tastiness of the tomatoes being grown. Now, personally, tomatoes do not taste good. I can't imagine how the tastiness is determined. They all taste like water to me. So let's take a look at this more complicated design. So take 12 tomato plants from a garden store or a farmer's market. In each of those, we're going to take 2 plants and look at them as a group. So the first group, we're going to grow 2 plants and say they are our control. So they don't get any water. Chances are they're not going to live that long. Our group 2 gets half dose of the fertilizer with no water. Group 3, again, all of these are from random assignment of what we bought at the store, gets the full dose of fertilizer with no water. So you can see as the more factors there are in a given treatment, the more groups we're going to need to have. Group 4 is our control that just gets water. Our group 5 is half dose of fertilizer and water, and group 6, full dose and water. And what we want to do is, after we grow these plants, compare juiciness and tastiness. If you want another controlled experiment, if you watch Good Mythical Morning, they recently, for Thanksgiving, showed people, is wet brine, dry brine, or no brine good? And they also compared, should you baste a turkey? Now, I could gladly post the video and link in the description of Good Mythical Kitchen, I think it is. And it's quite interesting to see this type of design developed in things that people consume all the time.
And that will bring moisture inside the turkey, but we also need a control that is not brine to see if that makes it juicy or not. Now, the second myth revolving turkey juiciness is basting. So that means you're taking either the turkey juices or an outside fat, and you are literally covering the skin in periodic intervals, typically 30 minutes throughout the cooking process. People say it locks the juices in. I'm not so convinced. So we're taking the wet brine, the dry brine, the control, and we are going to be basting half of the turkeys in the oven. My thought is that basting is really only a skin deep process, so we can create an even divide along those turkeys to really test out the process, see what combination yields the juiciest turkey.
Last thing, things that are behind the scenes that we can't control for, or that are mixed together that we can't separate out. This is what we get with lurking or confounding variables. So when the changes in the levels of one factor are associated with the changes in the levels of another factor, we say that these two factors are confounded. So let me say that again. When the changes in the levels of one factor are associated with the changes in the levels of another factor, these two factors are confounded. We can't separate them out. When we have confounded factors, we cannot separate out the effects of one factor from the effects of the other factor. Whereas a lurking variable creates an association between two other variables that leads us to believe that one may affect the other because we are unaware of the effects of the lurking variable. So a lurking variable is usually thought of as a prior cause of both y and x that makes it appear that x may be causing y. So, for example, let's pretend it's not December. Let's go 8 months into the future. Let's go into August. Fast forward in time. You collect data on sunburns and ice cream consumption. And you find that the higher ice cream consumption is associated with the higher probability of getting a sunburn. Does that mean ice cream consumption causes sunburns? Well, we know that they both increase, so there must be this confounding variable that is temperature. So obviously, when it gets warmer out, hot temperatures cause people to both eat more ice cream and spend more time outdoors under the sun, resulting in sunburns. Confounding can arise in experiments when some other variables associated with a factor has an effect on the response variable. So since the experimenter assigns subjects at random to treatments, not simply observing the treatments, and cannot separate out the associated confounding variable, the confounding variable has nothing to do with the assignment. So no matter how much we try to control for variation and randomize to mix things up, the confounding variable has nothing to do with the assignment. Because of the confounding, we cannot determine whether results found are caused by our factor or by the confounding factor, or some combination of both working together. And that is the problem. When we know that there's two things that are interrelated, we can't separate them, control for them, then we can't really make those cause and effect statements. So I try to keep the difference between lurking and confounding like this. Confounding is what happens when two variables are working together to affect changes. We may know about the connection between the two variables, but we cannot separate them. Think hot temperatures, ice cream, sunburns. Lurking variables, on the other hand, are usually unknown to the researcher. Thus, the effects observed may not be due to the variable the researcher believes, but unknowingly due to the variable hidden behind the experimental factors. Hence, a lurker. So let's just put this in a quick summary. At a glance, terms with which you should be familiar going forward. We talked about experimental units. Humans, we're calling subjects or participants. We have factors. We have treatments. So a group gets a treatment. The factors are what we are changing. We have our independent variable, often our explanatory or predictor variable, and we have our dependent variable or a response variable, our output. We looked at observational studies, whether they are retrospective, looking back in time, or prospective, they're looking at current day and age. We went through the 4 principles of the completely randomized experiment. We highlighted randomized block experiments. We also talked about matched pair experiments with blinding and placebos and the placebo effect. So let's just put this into a little bit of context. See if you can spot something wrong with this. In a Newsweek article, Newsweek magazine, what are those? Of all pre-college curricula, the highest level of mathematics one studies in secondary school has the strongest continuing influence on bachelor's degree completion. So the highest level of mathematics one studies in high school has the strongest continuing influence on the completion of a college degree. Finishing a course beyond the level of Algebra 2, for example, let's say trigonometry or pre-calculus, more than doubles the odds that a student who enters post-secondary education will complete a bachelor's degree. Interesting. Now, is there anything wrong with this statement? And I want you to think, is this an experiment? Or is this an observational study? Because if it's an observational study, then we cannot use any cause and effect or causal language. Now, if we did want to conduct an experiment, a question to you would be, how might we design a study to test this theory out? And are there any problems with doing this type of study? Think, if we are randomly assigning people to go through pre-calculus and other people stop at geometry, that's kind of playing with fate, isn't it? Especially if people want to continue on. So that's going to end our lecture notes for chapter 13 and for unit 3. In class this week, we are going to be doing this experiment on page 35. So I'm going to do my best to parrot this. So we would normally do it in class, but we're going to try it in our new way that we're learning right now. So thank you so much, Falcons, for your attention and your work. I really appreciate you, and I will see you in the next one. Peace.